Okay, YouTube, in this last video, we're going to take a look at what we refer to as slant asymptotes. And a slant asymptote, as opposed to a horizontal asymptote, you can see on this graph here, is just this asymptote that is slanted. It is an oblique line that just means it's not horizontal. And it's this line that our graph, as we go out to very large and very small x values, our y values are always approaching on the ends there. So this is, as a matter of fact, the graph of x squared plus 1 over x minus 1. And the top is not factorable. If this had been an x squared minus 1, we probably could have canceled the x minus 1 factor out. But right now it's stuck the way it is, and we get the slant asymptote right here. Now, here's the deal. The slant asymptote has this equation, y equals x plus 1, which is just a line. Our y-intercept is 1. And our slope is 1 over 1, so it goes up 1, right 1. You can see how they've generated this whole slant asymptote. My goal in this video is to help you learn how to determine what the equation of that slant asymptote is. So if you want the equation of the slant asymptote, here it is. And this only works with the slant asymptote. Let's make a little note here. Only ever get slant asymptotes if the degree of the numerator is 1 more than the degree of the denominator. This only ever happens if that's the case. And so that being said, basically what I want to tell you is if you want to find the equation of the slant asymptote, what you do is you take p of x and you divide it by q of x. I mean, you just really would just go divide this. And I'll show you here that I am dividing by a first degree thing. So if I were to divide x squared plus 1, which is 1x squared, 0x to the first, 1 constant, and put a 1 out here for my x minus 1 factor, check this out. I would get 1 times 1 is 1, 0 plus 1 is 1, 1 times 1 is 1, 1 plus 1 is 2, so this is my remainder. And what I end up with here is this, when I divide this by this. I got a quotient. Now my quotient here is 1x plus 1. This is what I get from just this part right here. But I would say that the slant asymptote is this y equals mx plus b, or in other words, in general, we always have the slant asymptote as equals y equals the quotient polynomial. That's always going to be the case. So if you have something on top that is second degree and you divide it by something that's 1 less in degree, which is a first degree, a second degree divided by first degree leaves us with this first degree thing down here that has this equation of the slant asymptote right there. So we neglect the remainder, by the way, and we just say just this part right here. This is your slant asymptote. Go for the quotient. So for this right here, it says find the slant asymptote of this right here. We have the second degree divided by first degree. I know this doesn't have a horizontal because our degree is heavier on the top than it is on the bottom. So we're going to say our slant is equal to the quotient of these two things. So what I'm going to do is I'm just going to put this together. We say 2, -5, and 7. I notice that I can do synthetic division here because I have a divisor of the form x minus k or x minus c. So we would say dropping our 2, we get 2 times 2 is 4, plus a -5 is -1. Times a 2 is a -2, and add these together I get 5, so that's our remainder. But really, remember, here's all I want, and I would say then our slant asymptote, I just want to show you how easy this is to find our slant asymptote, is just y equals this quotient polynomial right here. So we say y equals 2x minus 1 is the slant asymptote there. So just to go to show you that this is indeed the slant asymptote, what I want to do is this. We're going to go graph y equals 2x minus 1, which is just a line, has a slope of 2 and a y-intercept of -1. So 2x minus 1. So it hits at -1 and goes up 2 over 1, and we would have our graph here. So we say this is our slant asymptote, and how about we do this? We'll just make it dotted also. Dotted slant asymptote. Let's go put in our original function here. So we had a polynomial divided by another polynomial here, and I believe that in terms of what we had here on the bottom, we say, oops, x minus 2. So we have x minus 2, and on the top here we had 2x squared. I remember that part. 2x squared minus 5x plus 7. So minus 5x plus 7. But what I want you to see here is that as I zoom out, on the left and right side of our graph, our y values get really, really close to the value of the slant asymptote. Now, if I were to ask now, but where is the vertical asymptote on this graph? What is this value here of x that we're getting really close to? It looks like we're getting really close to a value of 2. I can even put this in, x equals 2, and we see that that is indeed the vertical asymptote. But that's only because when you set the bottom equal to 0, we get our vertical asymptote still. So this has a vertical asymptote. Let's see if I can click in the answer here. Not very easy to type this way. We say vertical asymptote at x equals 2. and a slant asymptote at y equals 2x minus 1. Cheers.